And we've had a lot of help this weekend. Lots of people were down. My dad came down this weekend. Josh is on the camera right now. Nate was here. Thomas was here. George was down. George's wife Stephanie came down and was fiberglassing with us. Now this is something that Thomas has been working on for a while. We've got a 1997 Metro transmission. Problem with the Metro transmission is it had it was 5-speed manual transmission. However, it had a solid rod for the shifter. You can see here where it goes in and out and turns to the side for selecting your different gears. Problem we had is we had to hook that. We couldn't make a straight line to our shifter, so we had to create mounts for cables, hook the cables to a new shifter bar that we made, and then hook it up to a shifter that we have in order to actuate the transmission. Now we're going all electric, BEV, battery electric vehicle. So you don't really need too many gears in your transmission. The electric motor is fairly efficient and can spin to high RPMs, 9 to 15,000. 15,000 is about the max for ours. But using this setup, we'll be able to increase the efficiency of our drive cycle by watching our eVision monitor, which tells us the exact amount of power we're drawing. While we're watching how much power we're drawing and we know the range in which our electric motor is most efficient, we'll try to keep it in that range. This gives us the option of switching gears to see if we can get just a little bit more efficiency out of it. When you're in town, you really do want a low gear. Electric motors are only about 80% efficient, some of them only 70% at low RPMs. You want to keep them up between about 3,000 to 6,000 RPM depending on the motor. So if you're in first gear in town, that's probably optimum. Second gear for about 45 miles an hour, but you'll need third gear if you want to hit 80 or a little more. And you know, sometimes we do want to go a little faster than the speed limits allowed, unless you're in Montana and there's no speed limit during the daylight on interstates. And we plan on test driving it there at some point because we really would like to know how fast it'll go. This is our battery setup. I must thank Dave at EV Components. He's been giving us a lot of help, a lot of sponsorship. You can see all the little, these are our batteries. This is one of the stacks of batteries. And you can see the Elition battery management boards that go across each of the cells and monitor the voltage. Well, we had a little problem with one of the wires and we shorted out a couple of our BMSs, the battery management cells. And Dave was very, very good to us and rushed us several new boards to replace the ones that we had a little issue with. And then he also got us these really nice, if I can find them, they were right here. They are now right here. Individual chargers. These charge individual cells. It brought a couple of our cells up to the voltage it needed to, so that while we're using our large charger, the more disparity in the cell's voltage, the longer it takes to balance the cells. If we use a couple individual chargers, if we find some cells that are low, and we had a couple 3 that were very low, and we're having troubles balancing them, we put the individual charger on it that has the built-in intelligence for monitoring the individual cells, charged them up, hooked them back in series, checked them up with the entire pack, and then everything was pretty good. And Nate did this all weekend. UPS just showed up Saturday morning. We had to sign for this. This is a specialty item from Europe. We had to find an opening for our water inlet for the battery case. All vehicles that have high voltage systems that compete in the Progressive Insurance Automotive X Prize must have a certain size opening to allow water to get into the vehicle or into the battery boxes to quench a fire. So a flood hole basically. And this is ours. We've got an aircraft fuel plug that has a 4-inch opening. Tapers down to 3.6 inches about when you open it up. This will be mounted in the center of the car, right above the tail end of the battery pack. This then will be piped down into the central pack, which opens up to the side areas. We have a T-shaped battery pack, the sides of which are opened to the two pyramids you just saw in the previous video. So if there is a thermal incident, which we do not anticipate, we'll be able to flood it with water and cool it down, bringing it back to a safe condition. However, we're using lithium iron phosphate batteries, not lithium polymer. The lithium iron phosphate batteries, the advantage to them over lithium polymer is the problem that you can get with lithium polymer batteries is the lithium is, when it hits about 200, if the battery hits about 270 degrees, the lithium can precipitate out of the polymer matrix which holds it in place. If the lithium comes out and then it's exposed to oxygen, lithium burns in an oxygen environment, and it will burn at over 3,000 degrees. If it hits that temperature, all the lithium in the polymer around it then is released from the polymer, is exposed to air, and ignites. That's how you get a cascade effect with the lithium polymer batteries. Lithium iron batteries, on the other hand, the lithium is molecularly bonded to the iron molecule. You have to get to over 3,000 degrees to break the bond. If any part of this car is at 3,000 degrees while I'm in it, my last concern is going to be that the batteries are going to catch on fire. I don't think I'm going to be anywhere near it.